Bien, donc après cette pause café, on va reprendre pour la deuxième session de la matinée. Et c'est mon ami Marc Barthelemy de l'IPHT qui va nous parler de la dynamique des cités et de la physique statistique des cités. À toi, Marc.
C'est en anglais, hein? Oui. Hi, everyone. Yes, maybe something different. Now, I will try to give you a flavor. I'm not going into many details, but just to show you, you probably don't know all this stuff, so all the physics and basically statistical physics can help to understand systems such as cities. So let me start with some general stuff. Very quickly, whatever your definition of a complex system, the city certainly is one. And you have many agents, you know, individuals, institutions, etc., interacting with each other on different spatial scales, on different temporal scales. So really, I mean, whatever really your definition of a complex system, here we have all the ingredients, heterogeneity, different scales, etc., to give rise to emerging behavior. And indeed, we see many emerging behavior, collective behavior in cities, and really, so congestion, mobility patterns, etc. And social segregation, I will talk about in a minute. And the problem is really, can we model the system? Can we say something quantitative? Can we make some prediction? And so far, this is still a bit unclear, in fact. So despite the rest I will talk about now. So this is really the problem. Can we understand, model the evolution of a city? So very briefly, the state of the art, so you have different approaches. Of course, urbanism, which is more or less quantitative, most of the time qualitative, so very political in general, so people have some idea about how a city should be and what you should do, etc. But this is really not scientific, in fact. There's a long tradition of economists, it's urban economy. Krugman, for example, is a well-known guy who did a lot of work in spatial economics. So the problem with this approach is that they work on very simplified model, which is nice, that we like as physicists, but very often the connection with reality and with data is very weak, as usual with economy, but especially in urban economics. There is a book which is called Spatial Economics. It's a 400 pages book. There's one page with data. So it's really to show you that these guys, they like to do mathematics, etc., but they don't care too much about reality. Now the big thing for some years now, but it's really growing strong, are agent-based modeling. And the buzzword right now is a digital twin. So just a word on that, because this is invading our lives, in fact. People are trying now to construct a digital twin of a city. So like Sims or whatever, you know, you put every parameters you have in a model, and you really want to duplicate numerically a city, which I think as a physicist in the tradition of physics is a crazy idea. And I think it's really doomed to fail. But these people, you know, and all the European grant calls, etc., are on digital twins about cities. So you have this buzzword, you know, smart cities, digital twin, etc. Yes? I've seen some attempt. It's, I mean, they're trying everything. So they're trying to predict, they are trying to describe. But, you know, the only attempt I saw, you know, are diverging after 15. You know, they tried, for example, to simulate what is happening in St. Pancras station in London. But after 10, 15 minutes, you see a divergence between the simulation and what is happening in reality. So here they really want to use it for planning, for everything, you know, for predicting the evolution of a city, etc. So it's really, I think, a crazy idea, but it's really the buzzword now. And in particular, when you see what happened in Paris with the closing of the Voie sur Berge, you had left-wing simulation and right-wing simulation. So Hidalgo was saying, oh yes, this is going to be fantastic, traffic is going to decrease, and Pécresse said, no, not at all, it's going to be a terrible mess, etc. So, and backed up with simulation, so to call, mostly consulting companies. But, and so, you know, but this is a difficulty, sorry? And this is even worse, is that we don't even know. We don't even know. That's 4 or 5, well, more, it was in 16, so 6 years after, there's no consensus if it was or not a good idea. So, and this was a well-defined problem. You take a segment of road in a city, you close it, what's the effect on traffic? So it's a well-posed problem, and we were not able to give an answer to that. So, you know, from there to construct a digital twin, I really have serious doubt. But no, because I think simulation is not the point here. The point is to get data. And there's a serious problem in France, and especially in Paris, about getting data. And the crux of the problem here is what we call origin-destination matrices. So you have to know where people live and where they're going to. And this is really the heart of the problem. And so if you want to say something smart, you need data first, not simulation. So so just very quickly, so as a physicist, what we want to do is to get the data, make some measurement, try to, you know that very well, what would be the minimal model with the largest number of prediction in agreement with data. So this is really the goal. So this is what we would like to do. Just a word about the future. There is an increasing number of people doing machine learning with some reasonable result, let's say, and this is especially true for systems as complex as cities. And I don't know about the future. It might be that this physicist approach, let's say, almost pedestrian approach will be prehistoric very soon, and that people will all do machine learning stuff. But maybe some hybrid, way is possible. But we'll see. Anyway, so more specifically, if you think about statistical physics and cities, in fact, there is a long story. And I will talk a few minutes about the Schelling model without entering details, but it's more for your, let's say, entertainment, let's say. And I will, in the second part, I will talk about some stuff I did recently for the growth equation for cities. But the Schelling model I will talk about in a minute is really, was proposed in 71. And this is really, as you will see, there's really a big flavor of statistical physics in it. But there's a lot of other stuff, such as diffusion, limited aggregation, fractals, etc. All the fractal stuff in the 80s got a huge success among geographers. And everybody was measuring the fractal dimension of the city, etc. So it was a big deal. And so you see already at that time some fractal models of cities, and percolation too came. And actually this is more specialized, but we have a big problem of defining what a city is. And there is a very interesting proposal to take it as the giant component of the percolation cluster of the built area, which is the most sensible definition of a city, actually. This was proposed some years ago. And then there are many other models, for example, to understand mobility, or people move from their home. Recently, so the most known model was called gravity model, so in reference to Newton, of course. But now we have some radiation model, etc., coming really inspired by physics and trying to describe all these phenomena. And so let me just to show you what this is. To me, it's really one of the first approach which is close to statistical physics, is the Schelling model. And at that time, the problem was to understand segregation in cities. And in particular, this was done in the US, the formation of black communities in cities, etc. And so this is what Schelling did. So it's a mathematical sociologist. It exists. And so he takes basically 3 states. You can be in the state +1 or -1. So these are the 2 groups, 2 ethnic groups, or whatever you like, and some vacancy, 0. And he did some simulation like that. This is a typical result of a simulation. And this is a very historical remark, but at the end of the abstract, he even says something like a general theory of tipping begins to emerge. And it's unbelievable because there are only 6 references here, which are, kind of, sociological reference. And it was published, this paper, at the same time of the book by Gene Stanley, Introduction to Phase Transition and Critical Phenomena. And at that time, really, you can tell that there was a wall between, the social science communities and physicists. Schelling had no clue about phase transition. He speaks about some general theory of tipping without even knowing what a phase transition is. And so it's really striking, how much the interdisciplinarity was really absent at that time. And so just to tell you a few words about the Schelling model, because of course it got a lot of interest among physicists and statistical physicists. You consider, so you divide, you take a lattice and you have this guy, an I, and you take his immediate neighborhood, and you look the fraction of different neighbors. So here you have 3 gray boxes, and so the fraction of different neighbors is 3/8. And the idea of the Schelling model is very simple, is that if this fraction is less than some value that you will call the tolerance, then the guy is satisfied, he's happy where he is, and he stays. So the spin stays +1, for example. And if the fraction of different neighbors is larger than this tolerance, then you move at a better place. So you take a place at random, and if it's better, you stay there. So it's not really a spin system. The spins are moving in some way, and they're trying to find a place, a location where they are happier. And what you see is that this is, for example, a more recent simulation made by these guys 10 years ago already. And when times evolves, you see that, in fact, you can observe some segregation. So you start from a fully mixed, let's say, population, and you let evolve the system, and what you see is that you see a segregated state, and that was the result by Schelling, in fact, even for relatively large values of the tolerance, which means that even if all the guys are on average very tolerant and they like to be with different neighbors, still the system at long times evolved to a segregated state. So that was the idea of Schelling, and this is why this paper is cited 6,000-7,000 times. It was really a demonstration of a collective phenomenon, even though the local guys are acting reasonably. So this model has been, if you are interested, I can send you other references. There's a nice paper by Matteo Marsili, who did a lot of simulation on this, and so really there's a lot of papers. There's even a very recent paper which appeared on the archive 1 or 2 weeks ago, and they introduced something new, because most of the variants of the Schelling model give the same result. But they introduced something. They introduced the probability to move, which is 1 over the time being satisfied, which makes sense. If you are for a long time at a place, then the probability that you will move, it's some inertia, if you prefer, will slow down the process. And in fact, it changes completely the universality class, so to speak. So the coarsening, the decrease is different of the density. You see, of course, aging in the correlation function that depend on the time you are making the measurement, etc. So there is an interesting connection with glassy system here. But it was just to mention that, so it's a very interesting system. So this was just to show you that, stat phys really, for cities, has a long history.
Here the states have their own private memory, right?
Yes. On a given site, the probability to move will depend, yes, absolutely. It decays. They took something which decays like 1 over the time you've been there. So let me go for the last 10 minutes to something I did recently with my PhD student, Vincent Verbavatz, which is about stochastic equation and cities. And I have to talk about something which is really like a pillar in the science of cities, which is the Zipf flow for cities. And I have to mention that it was first found by a physicist, Felix Auerbach, in the 13. And this guy had a very interesting, I encourage you to check the Wikipedia page. He did his PhD with Helmholtz. He studied with Kirchhoff, then Helmholtz. and he did a PhD on vocal sound, something like that. And so he had a very interesting scientific career. And he tried something in 1913. He sorted the population of cities, here for Germany. So you take a country, you take the cities, and you rank them. And the rank 1 is the largest city. And you consider the product of the population, here it's in 1,000, times the rank. And he noticed, and the product is this column here, he noticed that, okay, at the beginning it's moving a bit, but very quickly it's converging to some value which is relatively constant, here of order 50. Which means that for this country, the product population times rank is of order constant. And that's the first consultation, and this was generalized by Zipf, who published a long book on this, and he tried not only population in cities, but Zipf tried this for occurrences of words in books, for example. You count how many times the word, I don't know, two is appearing in Ulysses or whatever book you choose. And same thing, you plot the number of occurrences, here the population of cities versus the rank. So Auerbach did just a column, a table, but Zipf made a plot. And this is what he found, basically. This is in log-log. This is for the US, the metropolitan district in the US. And he found basically that for many, many systems, the population is decreasing with the rank, like 1 over R to some power nu, nu being very close to 1 in general. So this is exactly the Auerbach law, but let's say explicitly written. And this implies many things, of course, that, for example, the ratio of the first city to the second in a country is of order 2, for example. It also means that the population is distributed according to a law. A little calculation can show you that if you have this relation between population and rank, then the distribution of the population will be a power law for large values with the exponent 1 plus 1 over nu. Okay. Sorry? Yes, exactly. The rank 1 is the largest city. And you can do this with, in this book, Zipf did this with all possible things, And you always find some kind of power law. It's actually very used in linguistics also. You can see that there are some words appearing, the frequency with which appears a word in a text is very important, and Zipf discussed that also. Anyway, so yeah, of course, you have some fluctuations. The largest, they are a little bit, out. It's generally true. You have to go above. It's part of the problem, actually, but very quickly you see a power law. But what is happening for the larger city is unclear. And it particularly means that there's I don't have the time, but this is the simple demonstration to go from the population to the distribution. But if this Zipf exponent is over the 1, it means that the distribution of population is like 1 over S squared, which is far from a Gaussian. It's really a broad law. So cities in countries, they don't behave like a Gaussian variable, You don't have an average with some fluctuation. No, it's a very, very broad law. You have a long decaying, slow decaying tail, which is really against, it's not maybe shocking for you, but for an economist, for example, it was a disaster, because for an economist, all systems, particular city, has to converge to some optimum. If you make some cost-benefit analysis at a certain point, a city should reach an optimum, and this is, of course, not what we see. And there were even some conferences, why cities don't reach their optimum. Now, it's really the opposite of an optimum. It's a broad law. It also means that the largest city is of order the total population. In the sum of random variable, when you have broadly distributed variable, this is what is happening. So basically, all this, what amounts to the problem: can we write the equation for the time evolution of the population of a city? That's really, if you know how to write this equation, then maybe you can understand why you have the Zipf law and what is happening. And this is the point here. And so there are few attempts. Gibra in 31, ingénieur de corps des mines at that time, proposed that the growth rate is independent from population. So you write basically that the population for city I at year t plus 1 is the population at time t times a random factor larger than 1 in general. And this is the Gibra equation. But if you do that, the distribution will be log normal. You have a product of random variables, so this is a log normal law. You don't get the broad law with exponent 2, so or close to 2. So this is not consistent with empirical data. And Xavier Gabet, French guy, economist now, professor at Harvard, Xavier Gabet proposed to add a minimum threshold. So meaning that cities, their population evolve randomly, but not below a certain threshold, which is actually a strange assumption because cities disappear. But anyway, this is what he did in 1999, and this is related to a random process where you add some random noise here positive. This was studied by the probabilist Harry Kesten in 1973. You can also see it as a random walk when you take the log of these quantities. And basically, what happens, I don't have the time to discuss all the details, but basically what happens if you take this process with a reflecting barrier, then you get a power law with some exponent which actually goes to 1 for a very small threshold. So you assume that your barrier is at S min. This is the minimum population below which you cannot go. And you find that the distribution is a power law, and this mu is basically going to 1 when your reflecting barrier is smaller and smaller. So this was the state of the art in 2000 and the years after. Most of the people were relatively happy. You have a Zipf flow of order 1. The model is Gabet, meaning that you have to introduce a minimum threshold, and everything is fine. The problem is that after 2000, there was always a lot more data, and people tried to plot the Zipf, make the Zipf plot for all possible countries, years, etc. And what they found is basically here, this is the distribution of the exponent you measure, the exponent nu. And so the perfect Zipf flow would be at 1, let's say, but you see a large variety. And in fact, if you look into detail the literature, it's not always even a power law. It's an ugly thing, and the exponent depends on the fitting range, and there are many, many problems. And in fact, this was in 2017. You could, so 17 years after Gabet, you could really doubt about the validity of the Zipf flow. So the problem, so there was a new problem. What's going on? Why don't we have Zipf, and how can we understand all this mess? And this is what 5 minutes? Combien? So the idea is that we won't try to explain Zipf. You would like to start from first principle and write the equation, the evolution equation for the population of cities. And the main idea is here is that, in fact, you write that the variation of population SI of city I is given basically by 3 terms. First, there is some demographic growth, which is the balance birth death. That's fine. Then there's some international migration, which most of the time is extremely low. Okay, so that's the term you can forget about. And then there's some interurban movement. People from one year to the other one, moving from a city to the other one. So these are the 3 terms, and you can, again, forget about this international migration. And the point is that then you can write this first term as let's say, as some growth rate eta I, and here the interurban term is basically the balance people coming in minus people going out. So that's very simple. And the thing is that we can measure all this. So I skipped the detail, but we can measure this for many countries. It's not the data easy to find, but you can measure all this, and here is what you find. You find that this first term, the demographic growth, is indeed, can be written as this form, with eta, which is indeed Gaussian. So the growth, the typical growth, you have an average value which is non-zero, of course. It's the average growth of population. And you have some fluctuations, and the fluctuations are typically Gaussian. What is more surprising is if you look this term, this interurban term, I skipped all the details again, but you can write it as a sum of random variable, capital X, and these capital X are broadly distributed, actually. There's some power law, can be fitted by a power law. It's a broad law, actually. It's not Gaussian or whatever. Exponent is of order between 1 and 2, and that's the surprise. And it seems that, you know, so this is the positive part. So on average, it's 0, but you have some broad law for very large values, positive values, or very large negative. So you have sudden burst of migration from city to city. So long story short, the fact that you have a sum of broadly distributed variable, you can use the generalized central limit theorem, and which tells you that, in fact, this sum behaves as this as a variable distributed according to a Lévy stable law, which is not the Gaussian, usual Gaussian, with the parameter alpha and some other parameters. So then what you get in the end is this, is that the variation of population is indeed given by a first term, which is the usual Gibra term, let's say. It's really the random growth, you know, which steadily increases the population, plus a term which is here with this noise zeta I, which is not a Gaussian noise, but a Lévy noise, so to speak, on average 0, but which can have very, very large fluctuation. And so this explains why, in fact, its average is 0, and so if you make the crude assumption that you just forget it, you know, since on average it's 0, then indeed you recover the Gibra approximation. But this is very wrong, in fact, because you have this super large fluctuation coming from the Lévy noise. And these are really related to the shocks, let's say, people suddenly going to one city because there is a new activity. And this is what we saw, in fact, since cities are existing. You know, the gold rush in San Francisco, the population jumped from 1,000 to 25,000 in 1 year because all these people were there to find some gold. And so this is really what this equation describes. I don't have the time now. 4 minutes. Okay, the thing is that this is a stochastic equation with two noise, a Gaussian noise, a Lévy noise. These noise are multiplicative, so you have to give a prescription. The usual thing, I mean, the most natural thing here is the Ito prescription, so that you have first the population, the migration acts after. And in the Ito prescription, we don't have the exact solution of this equation. You can write some approximation for large population, and this is the kind of result that you obtain. And I'm not explaining everything, but the dominant term, m equal 1 here, is like 1 over s, 1 plus alpha. So the dominant term here is indeed given by a power law, and the exponent here is far from being universal. This exponent alpha actually describes these interurban migration. So it depends, in fact, how people are moving from a city to the other one. So it's not a universal thing. It's, of course, you know, not far from 1, but with fluctuation. And this would correspond to the Zipf law with exponent 1 over alpha. The problem is that if in this expansion you compare the second to the first term and see when the first term is really dominating, it basically never happens. Again, I skip the details here, but you really need to have super large population in order to see a clean power law behavior. And I will get back in 1 minute to what it means for the Zipf law. Of course, it's not enough to show that it reproduces something like the Zipf law. And actually, this was an interesting suggestion from the referee, which is very rare that the referee is useful, actually. So he said, yes, but why not look? You should look at the dynamics also. You know, Zipf law is not enough, but because the dynamics is actually interesting, and it's usually represented at what is called the rank clock. So basically, the radius here is opposite to the rank. So here's the rank 1. So this is Paris, which was, and the angle is time. So from 1876 to now, basically, Paris was the first city. But then you have, of course, some surprises. You know, cities that were nothing suddenly become important. Aigues-Mortes, it's La Grande Motte, I think. It's a station at the sea. And so you see some variation. In fact, if you plot everybody, these are the rank clock. This is what you see for France. So the rank is definitely not constant, you know. And the Gabet model actually would predict something very constant. So you don't have, once the dynamics of ranking actually is very stable in the Gabet model, while in the reality, you have, you know, some crazy turbulence, some cities that were, you know, number 10 suddenly become number 100, disappeared in the course of history, etc. So, and here, just, it's not a demonstration, but here with this Levy noise, you see some fluctuations, and you can even make this a bit more precise by looking at the probability to have a rank variation larger than a certain value. The Gabet model doesn't see any large variation of rank, so basically each city keeps its rank, but in reality it's not true. This is the French result, the French data, and this is the prediction of the Levy model. So in addition, this model says something about the Zipf law, but also is in agreement with the observed dynamics. And in fact, this is what why our paper was published. The referee was in the end satisfied with that. And so what does it tell us about this, you know, 100 years after, about Zipf law, you know, and tens of thousands of papers? So in fact, what we see is that what you measure will be a horrible thing, but it's not a universal exponent as I was thought before, you know. What we observe here, if you believe this expansion, is that if you see some exponent, some power law, it's the exponent governing the interurban migration, which is different from France to the US, to the UK, etc. It's this alpha exponent, which is 1.4 for a country, 1.6, etc. So for sure, if you see a clean power law, it is not universal. And moreover, the finite size effect, as I show you quickly, are super strong, which means that in fact the power law that you see is just a fit over many, many things. Finite size effect, noise, etc. And this, according to our result here, means that this measure of all the exponent is just a mix of bad fitting or fitting something which is not a clean power law. And this solves, I mean, in a not a nice way, but this Zipf problem for cities, it doesn't exist, in fact. So you have some complicated law. You still have some hierarchy, meaning a super large city, and the second largest city is much smaller than the largest one. And this comes because you have a power law distribution, but the exponent is unfortunately not universal. And with this, I stop. I thank you for your attention. Yeah, so I can.
Thank you very much, Marc. A question?
So I wanted to ask, the Zipf law, as you mentioned, appears in many other contexts, like linguistics or population genetics, etc. What about those other contexts?
I think Zipf did it indeed. He presented this stuff, you know, as very generic and general for many fields. But I think that now you have to look each field specifically, because here all this reasoning, the arguments, this is specific to cities. I don't have the same argument about, you know, migration of words between, you know. I think then it's a by case basis. I mean, you case by case basis. You have to look now. It seems that in linguistics, people it seems to be nicely verified. It seems to work very well. I'm not an expert in linguistics, but for sure, Zipf law seems to hold in linguistics. Here, it's unfortunately not the case for cities, but it also means that more generally, if you find some kind of Zipf law in the, I don't know, the Zipf, I think, looked horrible cases, you know, the number of deaths and wars, etc., you know, so, and he also found some kind of vague power law. But for sure, we cannot use, you know, the general argument, oh, it's a Zipf law, power law, it will come from the same mechanism. This result tells me that for each field, you have a different mechanism, and you cannot go to full generality, you know. Well, this is a personal opinion, but I don't know how you would transpose this in the linguistic stuff. Well, again, I'm not an expert.
So I had a question about this non-universal exponent alpha, which you said depended on interurban migration. Does it depend on some macroscopic parameters, like maybe area of the country or level of technological development or political regime? Do you have an idea?
This is of course the tough question. I mean, of course, I think it's more complicated than that, because when you see examples, you know, it's usually linked. I mean, the positive values are usually connected to the attractivity of the city. So suddenly there's a new industry, you know, mining industry, for example. You need a lot of workers, and then, you know, many workers are going there because there's some work. So this is the basic mechanism. So now, why should it be a power law with this exponent? Honestly, to me, that's the next frontier. I don't know. But I agree that here it's an empirical result. I don't have a theory for that. The good thing is that it's an optimistic message, in fact. I saw when Cédric Villani was here, it's not prescriptive, this result, but it tells us something, is that the fate of a city is not fixed. Because, in fact, you have this demographic growth, you know, which is random but with a trend, okay? But what changes really the rank of a city in your system are really these interurban migration, which means that it's the attractivity of the city. And this can be modified by different politics, by urban planning, etc. Look, the result of Detroit, who completely went down and came back. And so it's an optimistic message. The fate of the city is not written in stone by some random Gaussian growth, let's say. You have some, fortunately, the Levy noise, and this is the attractivity of the city. So if you are a mayor, it means that you can change. It's not because your city is not important now that it will be the same in 100 years. No. And so everything can change. And as we saw with remote working now, the big unknown for the future is for the first time in history almost, I mean, cities exist because people needed to be close to each other, which allows, you know, to be diversified, to exchange goods, etc. For the first time in history, for many jobs, we don't have to be close to each other. What will be the impact of this on the structure of cities and the population? That's really, of course, it's debated now, like, you know, in urban studies, it's the main subject, but no one has a clue. No one has a clue. It might change completely and act as a, you know, very repulsive effect and negative or positive for middle-sized cities, let's say. So it might change everything.
Hi. Have you ever looked or considered not grouping by country, in the sense that, I mean, like migration can occur between different countries, like in a very massive scale?
The migration between countries? No, sorry, I didn't.
Between cities.
No, but I mean,
like, I mean, what I mean is like building these histograms, but not taking only the data from a country, but between like cities that are actually connected in a way.
It seems that Zipf at a certain point works at different scales. And even if you take the planet Earth, you have a Zipf flow for the distribution of, I mean, if you construct the Zipf flow for all cities in the world, you get some Zipf flow, which is relatively stable, actually. It's impressive. There was a nice paper in Nature by Marc Barthelemy in 2010, and he computes the Zipf plot at different scale, in particular the global, the Earth. And you can, Zipf in his study, in his book, he looks also, you know, countries of South America, for example, or things like that. So he's grouping cities, and you observe the Zipf flow also. From the point of view of the equation, it means that what you define as system and is different. So external exchange are a bit different. Demographic growth is not changing. Then you have to redefine a bit the inter-urban migration, I would say, and which probably have the same statistic. I didn't look at the data, But it's relatively stable, so you should have some kind of invariance at a certain scale. The data is not always easy to get. That was the main bottleneck. But we expect to have a certain invariance, and these results to be, maybe the exponent alpha will change with the grouping. That might be the thing.
Maybe a last question. Okay, so I think maybe you can take Marc.
Thank you.